Welcome to the deep dive. Today we're aiming to sort of dismantle that neat little schoolbook model of the solar system.
Right, the one that looks like a perfect clockwork mechanism.
Exactly. We want to show you the reality. It's actually, well, pretty chaotic, complex, and full of paradoxes.
Definitely. And a great place to start is maybe the most common mix-up seasons on Earth.
Oh, yeah. Everyone thinks, oh, summer's hot. We must be closer to the sun.
It feels logical, doesn't it? But it's completely wrong.
In fact, if you're in the northern hemisphere, summer happens when Earth is actually farthest from the sun. That point is called aphelion.
Yeah, the distance change throughout the year is really tiny, doesn't affect the temperature much at all. The real driver is Earth's tilt.
That 23.4-degree lean we have.
Exactly. As we go around the sun, that tilt means different parts of the Earth get more direct sunlight at different times of the year. That's your seasons.
And where did that tilt even come from? It's kind of a violent story, isn't it?
Very violent. It's believed to be the result of the giant impact hypothesis. Billions of years ago, something huge, maybe Mars-sized.
Thea, they call it.
Thea, yeah.
Oh.
Slammed into the early Earth. That collision tilted our planet, and the leftover debris eventually formed the moon.
Wow. So our seasons, our moon, maybe even life itself.
Wow.
It all tied to this ancient catastrophe.
Pretty much. Cosmic accident, you could say.
Speaking of things not being what they seem, let's talk about the sun. We see it as yellow or orange, right?
We do, from here on Earth. But that's just an atmospheric trick.
Like a filter.
Sort of. Our atmosphere scatters the shorter blue and violet light waves. That's why the sky looks blue.
Yeah, okay.
Leaving the longer, yellower, and redder light to come straight through to our eyes. If you were in space, the sun would look basically white.
White, a blend of all the colors.
Correct. But the really weird thing about the sun isn't its color, it's the temperature.
Okay, go on.
Well, the surface, the part we see, is about 10,000 degrees Fahrenheit. Hot? Sure.
Yeah, sounds hot.
But its outer atmosphere, the corona, which is much thinner, somehow flares up to millions of degrees, like 3.5 million Fahrenheit.
Wait, it gets hotter as you move away from the main heat source? How does that even work?
That's the million-dollar question. Or maybe the 3.5 million degree question. Physicists are still trying to figure out the exact mechanism. It's a huge solar mystery.
Okay, let's jump to some weird planets. Venus first, the upside-down one.
Good choice. Venus is bizarre. For starters, its day is longer than its year.
How long?
A day on Venus takes 243 Earth days. Its year, orbiting the sun, only takes about 225 Earth days.
So a day lasts longer than a year. And it spins backward, too.
It does, retrograde rotation. Most planets spin the same way the sun does, but Venus goes the other way.
Any idea why? Another collision, maybe?
That's one theory. A massive impact could have flipped it or reversed its spin. Another idea involves its incredibly thick atmosphere.
The greenhouse effect one.
Yeah, that crushing CO2 atmosphere creates a runaway greenhouse effect, making Venus the hottest planet around 870 degrees Fahrenheit, hotter even than Mercury, which is closer to the sun.
Just scorching. Okay, let's head further out. Diamond rain. Is that real?
It seems to be, yes. On the ice giants, Uranus and Neptune. The intense pressure deep inside these planets could squeeze carbon atoms from methane into solid diamonds.
Actual diamonds raining down inside a planet.
It sounds wild, but the physics checks out. What's really interesting is the difference between the ice giants and the gas giants, Jupiter and Saturn.
What's the difference there?
Jupiter and Saturn are much hotter inside. So while diamonds might form, they could actually melt deeper down.
Melt? You mean like oceans of liquid diamond?
Potentially, yes. Vast, deep oceans of liquid diamond. On Uranus and Neptune, which are cooler, the diamonds probably stay solid and sink, maybe forming a layer near the core.
Mind blown. Okay, sticking with giants, Jupiter's great red spot. That's just a storm, right? But a persistent one.
Incredibly persistent. We know it's been raging for at least 150 years, probably much longer. And it's huge currently, about the size of the entire Earth.
One storm the size of our planet, that really puts things into perspective. The scale is just hard to grasp.
It truly is. You think about the planets, but the space between them is the overwhelming reality. The sun itself contains 99.86% of all the mass in the entire solar system.
Almost everything.
Pretty much. Here's an analogy. If the sun were a big sphere, say 24 feet across, Earth would be like a tennis ball, half a mile away.
Half a mile, wow. And the system goes way beyond the planets, right? To the Oort cloud.
Exactly. That's the theoretical boundary. A giant sphere of icy bodies surrounding everything, extending maybe 100,000 times farther from the sun than Earth is.
100,000 AU. What's AU stand for again?
Astronomical unit. It's the average Earth-sun distance.
Yeah.
So yeah, 100,000 times that far out, we're talking like 1.6 light years.
And all that space isn't truly empty, is it?
Nope, not a perfect vacuum. It's filled with tenuous plasma, the solar wind, plus the mysteries of dark matter and dark energy influencing things on larger scales.
And the whole system, sun, planets, Oort cloud, everything. It's all moving.
Oh yeah, we're hurtling through space, orbiting the center of the Milky Way galaxy at something like 515,000 miles per hour.
500,000 miles an hour.
Roughly. It takes us about 230 million years to complete one lap around the galaxy.
230 million years. What was happening on Earth the last time we were in this spot?
Dinosaurs were just starting to appear.
Incredible. So the big picture takeaway here, our solar system isn't this neat, static place. It's shaped by violence, ruled by complex physics, and just unimaginably vast.
That sums it up well. Chaotic history, complex mechanics, astonishing scale. And maybe the final thought to leave you with is this. Even the very start of our solar system wasn't gentle.
What do you mean?
The cloud of gas and dust that eventually formed the sun and planets probably didn't just collapse on its own. It likely needed a trigger.
Like what?
The shockwave from a nearby supernova, an exploding star. So, in a way, our existence here is tied directly to cosmic violence, right from the very beginning.
Wow, from a star's death came our sun's birth. That's quite a thought to end on.